Hello. So in this video, we're going to be talking about function composition. So function composition is one of those things that is generally really difficult in sort of pre-calc classes. I think by virtue of usually being taught purely symbolically instead of, again, with this context running. Because the idea of function composition actually is very natural to occur in the real world in context, okay? So let me sort of give an example as way of sort of motivating what function context is, and then we'll dive a little bit more into the actual mechanics and notation. So let's say you produce music, right? So you produce music. Now, on the one hand, as part of a music producer, your job is to sort of go through music, the raw music as it was given to you by the artist, and sort of help make it sort of studio sounding. You record it in the studio, you might do whatever it is that you're going to do in terms of sort of changing levels, remix, whatever. But at the same time, so that takes time, but at the same time, you need space and you may not have the equipment yourself, like own it yourself, so you may have to rent this kind of equipment. So we have sort of two things happening here. On the one hand, given an amount of, given a type of music, so if we have, say, M is the variable for a specific piece of music, then we could look at, let's say, T. So I'm going to maybe make it clear that it's a T. This is the time in, let's say, hours. And let's say C is the cost in dollars. And keeping in mind, I know nothing about actual, costs of these things, so I'm going to purely make up numbers here. So on the one hand, I could have a relation, really a function, because I have these contexts now, that sort of takes in the piece of music that I'm going to be working on, and the output of that relation, the output of that function, is the time and hours it takes to manipulate that sort of raw audio file to get it sort of ready to be put onto an actual, album or single or something. So I could have some relation that does that, some sort of work function. So let's say we have W, and as input for W, it's going to be sort of the set of all music, which I'm going to call M. I realize this is seeming abstract. Bear with me. I'm going to pull it back down to concreteness here soon. So this work function goes from all M to some positive real number. So it is definitely a real number. I'm going to use R. Okay. But really what it does is it takes a particular piece of music, right? The function takes in music and gives out some T, where T is the time and hours to produce that song. Okay, so this sort of relation is going from the set of all music, it's giving out some real number, some T, and that T value in particular is how long it takes to sort of mess with that particular song. On the other hand, I could have some overhead cost bit, right? Some studio cost. So maybe we'll call that S. And what S does is it takes in a time, so it takes in some positive real number. So I'm going to write sort of an interval here, 0 to infinity, not including infinity. Obviously, you can't have an infinite amount of time in there. And it's going to give out the cost, which again is some real number. Okay? And The way it does that is it will take in some time t, and it will spit out some cost. So cost for amount of time. Okay. Now this is very abstract. So let me give sort of a specific example here, such as I can, because I'm making things up, but a more concrete thing. So let's say I have a particular piece of music, M. I'm going to call it M is song A. Okay. And let's say that W of song A equals 15. So what does this mean? This means that, this means, i.e., it takes, whoops, if I could connect my brain and hand, this would go better. So it takes 15 hours to produce song A in the studio. Okay, so that's what I'm saying when I say W of song A is 15. It takes 15 hours to produce that song. And the studio, let's say I have S of 15 equals, let's say 4,000, which again means it costs $4,000 to rent 15 hours of studio time to work. Again, making these numbers up entirely off the top of my head. Now, I realize I talked about composition and it doesn't seem like any of that's happening. Bear with me, it'll happen. In fact, it's going to happen just in a second, but it may not be obvious. So as the producer, right, as the person doing this work, you may ask yourself, okay, how much does it cost to produce song A, right? How much money does it cost to produce song A? Now, I'm trying to relate money to a song, and I don't have a function that does that, right? My song thing only goes to time, and my money thing only comes from time. But sort of contextually, we know, right? Because if I want to know how much it costs to produce song A, well, to produce it takes 15 hours, and 15 hours cost me $4,000. So sort of mentally, we can think, okay, it costs $4,000. Right, connecting the dots. I'm going from song A took 15 hours, but 15 hours is $4,000. So song A through that 15 is $4,000. Bam. But what did we just, so that's what we did sort of conceptually. That was sort of thinking our way through, right? The numeric model type of approach. But mathematically, what did we do, right? So mathematically, what we did was we had one function that sort of went from the song to t, but then we could take the t and put it in here to get the answer we wanted, right? So in some sense, we were taking whatever this was whatever this was the output, right? This thing, the time it takes to produce song A, the output there, and put it as the input into S. And so this is exactly what function composition is. Function composition is composing functions in a way where you're taking sort of the output of one function and using it as the input in another function. So we could write this as, so again, this is sort of the concept thing. We could write this as, okay, we want the cost eventually. We want S of something. But the thing that we want to get the cost of is however long it takes for song A. which we know by applying W to song A. Meaning that this now is the input for S. Whatever the output of W is the input for S, right? So this is sort of one way of writing it. If we don't sort of use a particular song, if we ask how much does it cost for some song M, and I don't know what M is, right? Here I gave M a concrete thing, so we could do an example. What if I left it as M? Well, it would be S of, right, because I want cost, W applied to whatever that M is. Because whatever the output is, it's going to be a time. I can put that time into S and get a cost, right? So it's going to be however long it takes to work on the song, the cost of that time will be my answer. So this is a composition of functions right here. Sort of last but not least, in terms of the notation, I can write this as S applied to W of M, okay? So I'm going to, again, do some of my own editing magic here, erase a bunch of this stuff and sort of tackle this at a more, not more abstract, but a more mathematical approach, more symbolically, as opposed to this sort of more concrete version. Nonetheless, feel free to pause the video here and go through this and make sure it makes sense how we got 4,000 and why it is that we're sort of composing, as I said, what it means to take S of this thing and how this relates to that when we just look at a regular M, okay? So, with that, I'm going to do some quick magic here and erase all this stuff. So, abracadabra. All right. So, as was just mentioned, thinking about this from a sort of function standpoint for this producing music bit, right? So we had some function M that took in, so we had a function that took in M, right, pieces of music, went to R, right? We called this the work function, W. And then we had another one, the studio function, which took in some time interval, or some amount of time. So we used 0 to infinity, and again gave us a real number. But this was the sort of cost of doing some studio business. Okay. And we talked about how we can apply the cost, sort of the studio time bit, because the input here is effectively some time, and the output here is really some time. And since these sort of sync up in some way, we can apply this thing to get an output, and then use that output as the input to get the cost, right? So visualizing this as a math person leads to one of my favorite things ever, because this is honestly what we call it. I'm going to show you what we call the potato diagram. That is honestly what we call it. So the potato diagram is a way of sort of visualizing the process of how functions move between domain, codomain, and ranges. So if we look here, for example, we call it because we draw these funny looking little potato pieces. So if this is the set M, right? So this sort of blob represents all music. And then I have some other blob here, which is all real numbers, but really what I'm looking at is the sort of time piece. Really, so this really is all real numbers, because that's my codomain, but the output in some sense should be possible times, right? So really what's happening then is that W as a function takes something from over here. We call it little m, some piece of music, like song A from our previous thing. And it takes that, remember, I mentioned this in the set thing, we call it taking, but or sending. But really what I mean is, if I use m as the input, W then of m gives us some output over here, which is really some time t. Okay. But then, and I'm going to do this sort of weirdly, so bear with me for a second. I have another, and I would draw these identical if I could draw it all, but I have another all real numbers set over here. Man, that is terrible. I'm just gonna go ahead and make it look weird. It's fine. And I have, and I'm gonna sort of deliberately not write this part of the tail yet, so bear with me, I'm gonna write part of it here. I have s as a function which takes something over here and outputs the cost c for whatever that input was. Now here's the rub, and here's the thing I want to sort of make clear. On the one hand, so let me use this color again. The codomain for w is r, right? This is everything. Pi, negative e squared, sine of 27, all numbers are over here. But I'm not going to have, I mean, I could have something like pi minutes or pi hours to produce it. That would be a weird way to count it. I guess it's possible. But sort of, it's certainly not possible that it took me -5 hours to produce that piece of music, right? Even if I have to do nothing, that's still a 0. So the output here, even though its type is a real number, its codomain is a real number, the range of w so the range of w is, I'm going to actually just say is contained in 0 to infinity. Because there's probably in practice some largest amount of time you're going to actually produce, so it won't go up to infinity, but it would be something, right? I don't know what that number is. So it's within that range, certainly. It would probably be smaller. So that means that within all possible real numbers, there's some smaller piece that w actually lands in. So if I were to write the range of w, that would be here. Where outside here would be like -pi or -17, right? The stuff that you won't ever actually be able to attain because it's the negative stuff. And in fact, the range of w even doesn't include something sort of big and positive enough. I just don't know what that is. So this nebulous form is within 0 to infinity. At the same time, s doesn't use as its domain all real numbers. It uses only 0 to infinity. So I would draw some random thing here for 0 to infinity, but importantly, and this is very important, I know that whatever I draw has to contain the range of w, meaning this pink range of w is going to be within the domain of s. So whatever the domain of s is, it contains at least that. Okay? So s takes stuff from its domain and lands in r, where, again, the output of s, right, I'm not going to charge them -17, so the output, the range of s is actually still sort of a strict subset. It's a smaller piece of this. I don't need to care for this part, so I'm not going to worry about it, but it would be. So to be clear, this thing, this piece here is the domain of s. All right, so why is that important? Why am I making a big deal of this? Because when I try to compose these things, right, I did earlier, I claimed I did something like s of w of m. So what is that? And I also said, okay, this is s of w applied to m. And really, these are notated this way because these are sort of two equivalent but fundamentally different ways of looking at the same process. So if I look at s of w of m, what's really happening is I fix m, I have an m, right? I apply w to it, I land somewhere over here, some particular point, which I've labeled t, right? So this thing equals t. So if I apply s to that, really what I'm doing is, instead of sort of taking an arbitrary point, what I'm doing is I'm taking that point and seeing where it goes. So let me sort of erase this. Fix my circles because I'm crazy like that. Circles, curves, that's what I meant. So if I do w of m, I'm going to land over here at t. So here, this t is really w applied to m. Here, this c is really, so c is really s applied, right? S being applied to t. But I just said t is really w of m, right? So s applied to t is really the same as s applied to what t is, w of m. So in order to go from here to here, I applied w to m, and then I applied w to m, and then applied s to that result, right? So c is really just s of whatever that middleman was, but that middleman was really gotten by doing w of m. And that's how I get here. So that's really what this notation is saying this thing equals c, really because this middle piece is t. That was a terrible t as well. Yeah, clearly I need a break, sorry. So this middle piece here, all of this, was t, and then I applied s to that t to get to the c. Now, there is a, as I said, fundamentally different way I can look at this, which is equivalent. These are not sort of, I won't get a different answer. I can do either way, but it explains the difference in notation. Because the other thing I could do is say, okay, well, if I'm going to apply w and land over here, and then apply s to land over there, really, whatever I'm doing, it's going to go from here to there, right? This is just some middleman that sort of disappears in the meantime. I never really talk about t. I just go from whatever the input was to whatever the output was, and I never care what t was, right? So I could look at something over here. Some say, I guess it would be better to call it some like x or something, some other piece or some random piece, and track it all the way over to this thing, some other c. Actually, let me do it this way. Let me do, not x, but let me try m prime, m with a little tick, and I would get some c prime. So I could apply it to some point, and I get some point over at the end, some cost. But now I'm not applying w or s, because w only goes to this middle, and s only goes from this middle. I'm applying some long map to go all the way from the start to all the way at the end all at once. And what is that map? That function is applying w and s. So really what I'm doing, then, this function, just like that was s and that was w, this is called s of w. So that's the difference between these notations. This notation is emphasizing sort of the role of the middle piece, whereas this one is emphasizing the fact that I could sort of do this abstractly in the sense that I could just chain it, ignore the middle entirely, and sort of combine the two maps as the two functions as functions, and then apply them to a first point to get an endpoint, right? So the input here, just to make it sort of clear the two different methods, I'm going to call that m prime. I'm going to get some c prime here. So this notation is emphasizing sort of the values in the individual maps, whereas this one is emphasizing that I'm making a new map, a new function, and applying it straight from the start to get straight to the end, okay? So whichever way you do it, like I said, it doesn't sort of make a difference. Whichever one you like to do, you can do it that way. You need to be able to read both notations, though. You need to be able to recognize and deal with both types. I do want to get back to the thing I stressed earlier, because I sort of buzzed by it real quick, which is that the range of w, the range, not the codomain, is contained in the domain of S. And this is important because when I apply W, I need to get some output, T. I need to be able to apply S to that output, to that T. The only way I can do that is if that T is something S understands, if it's something in the domain of S, right? So it's important that whatever I get out for W is something I actually can put in for S, because if I landed out here somewhere, then S wouldn't know what to do with it. It would have no rule to keep going. And so this whole thing would break down. So it's really important that whatever you get out in practice, right, whatever the range is, not the codomain, because the codomain is way too big, right? Whatever the range is has to be sort of included in the domain of S. It has to be something that the domain of S can understand, right? It has to be in there so S understands it to keep going. Now, if the codomain is already sort of in the domain, you're home free, right? If I had written as codomain here 0 to infinity instead of R, I would know that has to include the actual range, and since the codomain is included, I don't have to worry about anything. It's already sort of done for me. Whereas if it's not, R is not a subset of this domain, then I have to sort of figure out if the range of W is smaller, which is why I had to do this little bit over here, okay? This also means the sort of one big kicker that tends to mess with students the most, which is that it is really important what direction you are composing in. So in a problem like this, and this is why the context bit I think makes a big difference, it becomes really clear that if I'm applying S to W, this makes sense because W is giving me the time, S is taking that time and giving me a cost. If I try to go the other way, I'd be trying to, so if I tried to do, instead of S of W, right, S applied to W of M, if I tried instead, maybe write it over here in a different color, instead of doing S of W, if I try to do W of S of T, right, I'm reversing the role. Now, if all you ever see this with is numbers, then this would be a thing, and it's hard to tell how it would relate to the other thing. Spoiler alert, it doesn't relate at all, which is sort of the point here. It's looking at this as context. Think about what this is saying. I'm taking in a time, I'm getting out how much it costs to run a studio for that time, then I want to take in the cost and see how long it takes to produce a music of cost. That doesn't make any sense, right? The input into W is supposed to be music. And so the fact that S is outputting a number, a value of money, right, a cost, means that W doesn't understand that. W only understands individual pieces of music and tries to give you how much time it takes to produce that music, right? So it's really important that you get the order correct, because flipping the order turns the entire thing into total nonsense most of the time. And it's rare that you can flip the order and get something that even works, let alone something that might be similar. It's almost never the case that they're the same. In fact, in some very special cases, it is the same. And in those special sort of circumstances, depending on what it is when you do it, you actually get important information out of that. That's a whole other thing that we'll talk about later. So like, there are special circumstances where you test both of them, but it's because it's such a rare property that you would sort of look for that. It's almost never the case that that's true. Okay. So with that is sort of function composition in a nutshell. So we'll hopefully do examples and stuff in sort of the text and or another video if I have time, as well as problems, discussion, etc. Okay, but this is sort of the big picture. All right, and with that, we are done.